So having described this basic global predictor, I'm now going to look at the next form of a correlating predictor, which is called a local predictor. Okay, so I'm going to motivate this local predictor by going back to that for loop example that I had before. And to simplify the discussion, I'll assume that this is a for loop that executes 5 times. Okay, so at the end of it, there's a branch which evaluates the condition and then loops back up. Okay, so if you look at the branch history pattern, it would look something like this, right? The branch is taken 4 times, and then there is a not taken. Then it is taken 4 more times, then not taken, then and this pattern keeps on repeating. Okay, so our earlier branch predictors, the 1-bit bimodal and the 2-bit bimodal predictor, they were either trying to capture what the branch did last, or they were trying to capture the common case. And based on that, we got accuracies of 87% and 93%. Okay, and this is because, every once in a while this branch does something different. It does a not taken outcome, and so capturing the common case ends up yielding a wrong prediction for these particular branches. Okay, but if we had a little bit more information, right? So let's say that I knew that I was at this branch, that I was at this particular branch over here, and if I knew what this branch has done recently, I should be able to say with certainty what it's going to do next. Okay, so let's say that I have a history, and let's say this is a 5-bit history, and this would tell me that this branch in the recent past has done this. If I could see this additional information, I can say with certainty that what the branch is going to do next, it's going to be taken. Instead, if I could say that if I'm at this branch and what it has done recently is 0, 1, 1, 1, 1, then I can say with certainty that what it's going to do next is a not taken outcome. Okay, so having some history for this particular branch can really help. Okay, and this is different from what I described for the global predictor, where I was keeping track of what every branch, including all the neighboring branches, had done. Now all I care about is history for this particular branch, and I don't want to I don't want to adulterate that information with what other neighboring branches are doing, because this is a very regular branch. As long as I know what this branch did recently, I should be able to make a very precise prediction. Okay, so now this is what I'll end up doing. So here's my branch PC, and I now have 2 tables. There's a level 1 table, and there's a level 2 table, which is my usual saturating counters, right? So this is a 2-bit number, which tells me what is the common case. And what is now changing is how I'm indexing into the table, right? So if this has 16k entries, I ultimately need a 14-bit index. Okay, and how am I generating this 14-bit index? So I first use my branch PC to index into the level 1 table. This level 1 table has 64 entries, which means I need a 6-bit index to look it up. Okay, so I pick out 6 bits of branch PC, and I use that to index into this first level table. And what each entry over here is tracking is a 14-bit history for that particular branch. Okay, and again, as before, you can have aliasing. You can have 2 different branches with the same 6 bits that map to the same entry. And if they do that, then this history will keep track of what both branches have done recently. So that leads to some form of adulteration, some form of interference, and the predictions won't be very good. Okay, so my hope is that I have enough entries in my L1 to minimize these interferences. Okay, so let's assume for now that there is no interference. So this branch maps over here. It has its own entry in this table where it records what that particular branch has done in the recent past. Okay, so based on that 14-bit history, I will now index into this table saying that if I have seen this recent 14-bit history, this is what I'm likely to do. Okay, so based on that history, I will look up the counter, which tells me what is the common case outcome given this input. Okay, so again, there can be aliasing because 2 different branches, so some other branch could map to this entry over here, and if it has seen the same 14-bit history, then it too will map into the same location, right? So again, you will end up confusing the predictions for these 2 different branches. So the hope is again that you will somehow reduce aliasing. One way to reduce aliasing is to use a structure like the one I'm showing you over here. Okay, where for my level 2, I'm assuming that there are 1k entries, so I need a 10-bit index that feeds into it. How do I generate this 10-bit index? So the first thing I do is, for my level 1, I have 64 entries, so I pick out 6 bits of branch PC going in over here, and what I'm maintaining here is a 10-bit history for that particular branch. Okay, so out comes a 10-bit history. I then XOR it with 10 bits of branch PC. So I'm using 6 bits of the branch PC to look up level 1, and then using 10 perhaps different bits of the branch PC to to compute my index for level 2. And this index is being computed by XORing the branch PC and that particular 10-bit history. Okay, and this helps me, discriminate between two different branches that might have, similar history patterns. By doing the XOR, I'm making sure that those different branches and their patterns map to different entries in my table. Okay, so this will hopefully reduce the chances of interference. And each branch will now have lots of entries in this table corresponding to it, right? So one given branch, depending on the different kinds of branch histories that it encounters, you could have any number of entries in this table, right? So if you're keeping a 10-bit local history, if that 10-bit local history is all over the place, then you could have 1024 different entries in this table that might represent information for this given branch. Okay, but as we saw for the for loop example, there are only some particular patterns that end up being very common for a given branch. Okay, so the common case is that only a few entries in this table might correspond to one given branch. Okay, so this is how we are using information about the recent past, and not just looking at the common case, but actually looking at what is the recent pattern. Was it 11101, and correspondingly I keep track of the common case for that given pattern. Okay, and a local predictor just focuses on what one given branch has done, which will work really well for loops. And then the global predictor keeps track of what every branch in the program has done recently, right? And that might work very well for programs where the behavior of each branch depends on what the neighboring branches might have done. Okay, and these local predictors work well for some codes. The global predictors work well for other codes. Local predictors take a little bit longer to warm up, because for every single possible pattern for a branch, you have to keep track of some history to learn what that is likely to do. Okay, whereas a global predictor takes a little less time to warm up. Okay, so there are these pros and cons where there are certain situations where local predictors do well, certain situations where global predictors do well. There are even other situations where bimodal predictors do very well, where just keeping track of the common case can really help you out. Okay, so based on this observation, people have also designed what is called a tournament predictor. Okay, so since local predictors do well sometimes and global predictors do well sometimes, you implement both of these, right? So I have a local and a global predictor implemented, and then I have a third predictor which tries to tell me which of these two predictors happens to do better in the common case. Okay, so this is built just like any other branch predictor, and let's assume that this is a bimodal predictor, right? Typically these predictors make a 0-1 prediction which tells me taken or not taken. In this case, the tournament predictor produces a result that tells me, just as before, 0 or 1, but that refers to whether I should choose the local predictor or the global predictor. And this is trained in just the same way, right? So I'll look at the recent past and I'll see, who tends to produce better outcomes. Accordingly, I'll increment the saturating counter over here, saying that, the local tends to be better, pick the local prediction. Or I'll decrement the counter every time the global predictor is right and the local predictor is wrong, indicating that the prediction I should pick is the global prediction. Okay, so this local predictor will yield a prediction every cycle. Similarly over here, and this tournament predictor goes into this multiplexer saying, of these two predictions, let's pick the local predictor because that happens to be the better prediction. Okay, so with and these are predictors that are actually implemented in real process. Okay, so with all of these innovations in place, we started with something very naive, where my default was that I would just go to the next sequential instruction. So in my example, there was like a 10% branch prediction accuracy. We went to the 1-bit predictor, which went up to 87% accuracy. Then the 2-bit predictor, which went up to 93%. And now I'm just making up numbers, but it's possible that a global predictor takes you to 94, local takes you to 95, and then a tournament predictor designed very well will get you pretty close to 96%. Okay, so if you look at modern literature, the very best and most fancy branch predictors have accuracies in this range, and they often implement multiple different predictors and then try to pick the best of these many options. Okay, so when I was discussing all of these predictors, I was just focusing on the binary prediction, 0 or 1, taken or not taken. Okay, so if the branch is not taken, then it's simple. It's very easy to compute the next PC. It is simply PC plus 4. If the branch is taken, then I need to figure out where this branch is headed next. Okay, and that is usually done with a separate predictor which just keeps track of, a PC and where it tends to jump to. Okay, so there is a separate structure called the branch target buffer, which keeps track of where branches tend to go. So every time the branch is predicted to be taken, then you have to look up the separate branch target buffer and estimate what is the next PC.